Hello friends, welcome back to this series on the physics of solids. In the last class, we discussed about Miller indices. There we defined the Miller indices and we saw how to evaluate Miller indices, how to designate a given plane with an appropriate HKL indices. If you remember that the Miller indices is normally designated by H, K and L letters. Also, we summarized on the different fundamental features of Miller indexes, index based identification of crystal planes. In this episode, we will primarily discuss on the reciprocal lattices. We will define the reciprocal lattice and see the construction of a reciprocal lattice. Aim would be to deal with unit cell of reciprocal lattice in one of the coming episodes. But before discussing on the reciprocal lattices, let us draw your attention to the Miller indices of cubic lattices such as simple cubic, body centered cubic and the face centered cubic. The idea is to have a recap of the Miller indices so that we can go into the reciprocal lattice with a better understanding of the Miller indices. Now, as you must have studied in your earlier classes that simple cubic, the face centered cubic, otherwise FCC, the body centered cubic or the BCC are some of the fundamental primitive lattices. I am not getting into the definition of the primitive lattices, which you must have studied or go into the appropriate references. Now, as you can see in this figure, I have shown the primitive lattices of three different lattices: the simple cubic, face centered cubic and the body centered cubic. So, a cubic lattice is having only the atoms at the corners. So, as you can see in the figure, I have plotted there the planes of the typical planes of a simple cubic lattice. The 1 0 0 planes, which we defined earlier in our in one of the episodes, is touching all the atoms in the corners. Now, another possibility is to have diagonal planes, which we have designated there in the figure there as 1 1 0 planes. Also, in addition, one can always think of the planes such as 1 1 planes. So, a simple cubic, if you take the XRD or the neutron diffraction of a simple cubic lattice, necessarily it would have three different set of peaks of 1 0 0 plane, 1 1 0 planes and the 1 1 1 planes. Now, how the situation will be different in a face centered cubic? So, again as shown in the figure there, naturally you have the atoms in the corners, which are designated by the 1 0 0 planes, or here in this case you can have again you will have different set of parallel planes, but there could be a confusion that can it be called the 2 0, how can you define a 2 0 0 plane? So, necessarily if I take only one single cube to start with, the 2 0 0 plane will be those atoms which are at the face center atoms. But as I told in the previous episode, in the crystallography there is nothing like a permanent origin or a permanent starting point, it is all arbitrary. A person, a crystal who is having atoms at the corners can be a set of atoms which are defined to be in the corners can always be defined as the atoms in the face centered cubic in at later stage of the observation of the lattice. So, but necessarily a face centered cubic will have a 1 0 0 plane and in addition there will be 2 0 0 plane. So, if the 1 0 0 plane is about the atoms in the corners, the 2 0 0 plane will be made of the atoms in the face centered positions. And similar to the case of the simple cubic, here also you can have 2 to 0 planes also. this again the 220 planes will be again made of the atoms in the face centered position, and then again you can have similar 1 planes also. And now the body centered cubic. So, body centered cubic is bit more complicated, because you have only one atom additionally at the center point of the simple cubic. So, there here the 200 plane will have lesser number of atoms compared to that of a face centered cubic, but it will be made of the atoms in the body center, and also you can have 110 planes and the 222 planes. So, that forms a recap of the Miller indices for a basic fundamental cubic lattices such as simple cubic, FCC and the BCC. So, it should be a practice that whenever we get into the nuances of crystallography, we get a better understanding of the Miller indices, which can be of a better of a detailed discussion with the help of your references or for a higher class of delivery. So, now we get into the today's discussion topic of discussion, which is the reciprocal lattices. In the beginning of this series, I have defined two different lattices. One is the direct lattice and the reciprocal lattice. So, direct lattice, in some literatures you will see it as the real space lattice also. So, every periodic structure has two lattices associated with it. The first is the real space lattice, and this describes the periodic structure. The second is the reciprocal lattice, and this determines how the periodic structure interacts with waves, which we discussed already in the earlier episode. In this connection, we have discussed about the Miller indices. The Miller indices planes, when arranged sequentially, themselves form a 3D lattice, which we have already talked about in the last episode. And this 3D lattice will give rise to an elegant construction of what we call as the reciprocal lattice. There we talked about the H, K and L as indices developed based on the intercepts x, y and z on a real lattice with basis vectors A, B and C. But for this episode, I have to slightly change my basis vector designation for the easiness in carrying out the vector mathematics. Now, earlier what we defined as the A, B, C, now I take the permission from you to make it as A1, A2, A3, as you can see in the figure there. A, B, C is exactly same as A1, A2, A3. So, A, B, C was earlier the basis vectors for the real lattice or the direct lattice. So, now it is A1, A2 and A3. The orientation of planes in a lattice is specified by giving us Miller indices. It leads to description of planes by a vector normal to the planes. So, that is the beauty of the Miller indices. So, a set of parallel planes can be represented by one single designation or the Miller indices. That is the beauty of the Miller indices. But what is that? What is the characteristic of that direction of that plane? It is actually described by a vector which is normal to all those parallel set of planes. As I told, the planes themselves are part of a direct lattice, but when we put the vectors normal to those parallel planes, it generates a new lattice which we call as the reciprocal lattices. So, now once we have the reciprocal lattice vectors B1, B2 and B3. So, I take I call the reciprocal lattices by the numbers by the letters B1, B2 and B3. And with the help of this B1, B2 and B3, one can construct a reciprocal lattice. A family of planes are associated with a shortest reciprocal lattice vector, which I call as the G. So, G is the reciprocal lattice vector, which is the shortest reciprocal lattice vector. It is defined as G is equal to H B1 plus K B2 plus L B3, where B1, B2, B3 are the reciprocal lattice vector. One of the other ways in which we can define a reciprocal lattice is to define its connection with the real lattice. So, now we are dealing with reciprocal lattices. Earlier we are having originally a direct lattice, which was designated by, say, if I call the reciprocal lattice vector, the direct lattice vector by R. So, then in terms of my basis vectors A1, A2 and A3, I can write R is equal to N1 A1 plus N2 A2 plus N3 A3. Now, what is the connection between the reciprocal lattice vector, and the real lattice vector? So, the connection is E raised to I G dot R is equal to 1, where G is the reciprocal lattice vector, R is the real lattice vector. So, it is very clear from that expression itself that G dot R should be 2 pi n, where n is a integer, as you can see in the screen over there. So, this expression can be satisfied if G is expressed in terms of reciprocal lattice vectors Bi, which are defined as B1 is equal to 2 pi into A2 cross A3 divided by A1 dot A2 cross A3, B2 is equal to 2 pi into A3 cross A1 divided by A1 dot A2 cross A3, and B3 is equal to 2 pi into A1 cross A2 divided by A1 into A2 cross A3. So, and all together G is equal to H B1 plus K B2 plus L B3, and one should always remember that B1 is perpendicular to A2 and A3, and it goes, all these relations goes on in a cyclical manner. So, these are the three relations are as shown in the screen there, B1, B2 and B3. So, this expression is very important, especially when we are trying to evaluate the reciprocal lattice for any lattice, which we will be doing some of the examples in soon. Note that B2 and B3 are given by cyclic permutations of the expressions for B1. From this expression, it may be seen that the real lattice basis vectors and the reciprocal lattice vectors satisfies the relation Bi dot Aj is equal to 2 pi into delta Ij, where delta Ij is the famous Kronecker delta. So, in the one you will be knowing that the Kronecker delta will have a value of 1 when I equal to j, or I not equal to j will have 0. So, Bi dot Aj is equal to 2 pi into delta of Ij. Now, having said or having defined what is a reciprocal lattice vector, the reciprocal lattice vector, and what is a reciprocal lattice and what is the use of it, let us try to construct the reciprocal lattice. As we did in the case of Miller indices, where we started with a 2D lattice and we progressed slowly into 3D lattices, in the case of reciprocal lattice also we will do the same thing. So, as you can see there are two figures given side by side. In the left side you will be seeing a real lattice, and the other side you are seeing a reciprocal lattice. So, both of them are two-dimensional lattices. So, let us try to plot different set of parallel planes for the real lattice. So, there you can see the first set of parallel planes, which are represented by green set of lines. So, what is the corresponding reciprocal lattice for them? as we told in the earlier discussion, it has to be got with the Miller indices, or it has to be direction perpendicular to the all these parallel planes. So, this blue arrow over there represents the all the parallel planes which are in the real lattice. And now the question is that can we think of more set of parallel planes in this in the real lattice. So, there falls another set of parallel planes. So, what is the reciprocal lattice for them? So, it will be a different set, it will be a different reciprocal lattice vector as seen in the figure, and we can think of more such set of parallel planes in the real lattice. So, this red lines over there, there is another set of parallel planes, that is again represented by a single line or a single plane which is there in the reciprocal lattice. So, then that is the fourth set of parallel planes, and then you have another set of another reciprocal lattice there. So, there are certain ground rules which the reciprocal lattice follows. Three of them which I can remember very easily is, when a crystal is made to rotate, both the direct and the reciprocal lattice rotate, which is very clear from the understanding of the reciprocal lattice. So, when a crystal is made to rotate, both the direct and the reciprocal lattice rotate simultaneously. The second point which comes to my mind is that the dimension of the reciprocal lattice vector is length inverse, which is very important in physics, because there are two things which are very important in physics to understand for any parameter. One is its dimension and another is its unit. So, for a reciprocal lattice vector, the dimension should be length inverse. And the third characteristic which I can think of is that the volume of the reciprocal lattice is inversely proportional to the volume of the direct lattice, which means that a higher the volume of the direct lattice, it will be lesser, higher the volume in the direct lattice, lesser the volume in the reciprocal lattice. So, normally in the literature which is associated with the solid state physics, you will see something called the K space, which we will be also discussing, taking up the K space in when we start discussing about the interaction of the electric field with the crystal in some later part of our series. So, the direct lattice and the K space, the reciprocal lattice space, are related by its Fourier transforms. So, if we need to mathematically calculate the reciprocal lattice vector for a specific direct lattice, the easiest way is to take its Fourier transform. And as you know, the concept of unit cell, I am not trying to explain it over here, the concept of unit cell is very much central to the crystallography. And one of the things which you might have studied when you studied about the in the initial class of crystallography is that the unit cell of a direct lattice or a space lattice should always be a parallelepiped, which means that all the sides which constitute a unit cell should be parallel to each other. But one of the difference in the reciprocal lattice is that the unit cell of a reciprocal lattice need not be a parallelepiped. So, that is another characteristic which is offered by the reciprocal lattice. Now, let us try to calculate or evaluate reciprocal lattice of few fundamental lattices. Let us start with a simple cubic lattice. Now, the first and foremost question is that if you need to calculate the reciprocal lattice of any lattice, the first question is that what are its primitive lattices. So, what is the primitive lattice of a simple cubic lattice? So, we are talking about the A1, A2, A3. We have shifted from the ABC value. So, if I simple cubic, the primitive primitive lattice vectors could be defined as A1 is equal to Ax, A2 is equal to Ay, and A3 is equal to Az. So, what is A? A is the lattice vector, which is the dimension of one side of the cube. So, x, y, z directions. So, we need to calculate the reciprocal lattice vector for this primitive lattice vector. So, what was the formula which we discussed? B1 is equal to 2 pi into A2 cross A3 divided by A1 dot A2 cross A3. So, we try to evaluate the B1, B2, B3. So, here what is the B1? 2 pi into A2 cross A3. How much is A2 cross A3? Ay cross Az, which is equal to A squared into x divided by A1. A1 is A into x. So, Ax dot A squared x, which one can evaluate it as 2 pi into 2 pi divided by A x. So, the reciprocal lattice vector B1 corresponding to the primitive lattice vectors of a simple cubic is 2 pi by A into x. So, similarly, if we calculate B2 and B3, it will come to be B2 is equal to 2 pi by A into y, and B3 is equal to 2 pi by A into z. So, these three defines the reciprocal lattice vectors for a simple cubic lattice. Now, if I ask you what will be how will this reciprocal lattice vector look like? So, what will be the answer? The answer would be very clear if we evaluate, if we look into these three numbers very closely. You can see that the magnitude of all the three B1, B2 and B3 are exactly the same, which is a representative of the 2 pi by A, which means that we are again going into a situation of a simple cubic lattice. Only difference is that there the dimension was A, now in the new reciprocal lattice the dimension is 2 pi by A. So, when I told about the description of the reciprocal lattice vector, we have already put a hint into this situation that the higher the volume of the direct lattice, it will be in the reciprocal lattice, the volume will be the inverse or the smallest for that. So, similarly, higher the A, smaller the dimensions of the reciprocal lattice vector. So, the primitive lattice of a simple cubic is again a simple cubic lattice itself. So, that is the first evaluation. Now, let us try to evaluate the primitive lattice vector, primitive lattices for a BCC lattice. Now, I need to provide you with two important clues in that regard. We all know what is a BCC and an FCC means by. But when we learned about the lattice vectors of a BCC and FCC, when we defined them, we were not necessarily discussing about the primitive lattices. We were discussing about the non-primitive lattices in those cases, because what is the one fundamental characteristic of a primitive lattice? Primitive lattice, there should be only one lattice point per lattice in a primitive lattice. So, therefore, if we redesign the BCC and FCC, the primitive lattice vectors of a BCC and FCC are quite different. So, how do you define that? So, that will form a clue for you to understand the to understand the reciprocal lattice of a BCC or the FCC. The reciprocal lattice vector and the primitive lattice vectors are A1 is equal to 1 by 2 A x plus y minus z. A2 is equal to half A into minus x plus y plus z, and A3 is equal to half A into x minus y plus z. It is very easy to remember. There is this, you can see this negative points which are going in a cyclic manner. So, this is the primitive lattice vectors of the BCC, but at this juncture I should be telling you the primitive lattice for the vectors for an FCC also. So, that is helpful for you when you try to evaluate by yourself the primitive lattice vectors for a FCC. So, what are those? So, A1 is equal to 1 by 2 A x plus y, A2 is equal to 1 by 2 into y plus z. Sorry, I forgot to put A there. So, A1 is equal to A by 2 into x plus y, A2 is equal to A by 2 into y plus z, and A3 is equal to A by 2 into z plus x. So, these are the primitive lattice vectors for the FCC. Now, if we need to evaluate the reciprocal lattice vectors for BCC, how will you do that? We again take up the expressions. B1 is equal to 2 pi into A1 A2 cross A3 divided by A1 dot A2 cross A3. So, what is the A2 cross A3? Is equal to A squared by 4 A2 cross A3. If I define it in terms of I, j and k, that will be minus 1 plus 1, 1, 1 minus 1 plus 1. So, how much it will be? A squared by 4 into I into plus 1 plus 1 minus j into minus 1 minus 1 plus k into 1 minus 1, which will be A squared by 4 into 2i plus 2j. So, A squared by 4 into 2i plus 2j, which is A squared by 2 into I plus j. So, that is the A2 cross A3. So, how much will be A2 cross A3, and A1 dot A2 cross A3 is equal to A cube by 4. So, A2 cross A3 is equal to A squared by 2 into I plus j, and A1 dot A2 cross A3 is equal to A cube by 4. So, now we substitute that for the B1. So, B1 will come to be 2 into 2a into I plus j, and correspondingly you will have the B2 and the B3, which you can evaluate by yourself, and And now the same question exists as we did for the simple cubic lattice also. So, what will be the shape of the reciprocal lattice for a BCC lattice? Now, you can clearly see a simile between B1 and A1 of the FCC lattice. So, they are similar, and if we calculate B2 and B3 by yourself, you will be getting clear that it will be clear to you that the reciprocal lattice of a body centered cubic lattice will be a face centered cubic lattice. So, that is it. So that is how we calculate the reciprocal lattice of different lattices. So, the evaluation of the reciprocal lattice vectors or reciprocal lattices for another set of primitive lattices would be more complicated because of the more complicated arrangement of atoms in that, which needs a more time consuming evaluation of that. So, in this lecture we have tried to define a reciprocal lattice, and we also discussed about its connection between the reciprocal lattice vector and the direct lattice vector, and also we saw few examples of the construction of a reciprocal lattice vectors or the reciprocal lattices based on the primitive lattice basis vectors. Now, the task would be to go one step ahead in terms of evaluating of the Brillouin zones, which are the unit cell of the reciprocal lattice, which we will be discussing in our coming episode of this series. So, thanks for your patient hearing, and see you next time.